Okay, so my name is Zach Austin. I'm going to be your professor for this course. And today we're going to talk a little bit about uh, our first lesson for functions and modeling. This is going to cover section 1.1. It's all about kind of the vocabulary that we're going to be using throughout the course. You'll notice I have this set up here where I have my graphing calculator over here. I'm not really going to use that in this first lesson because it's more about an introduction to very important concepts we're going to talk about throughout the course. Okay, so I'm going to do some vocabulary first to get started, and then we'll use that vocabulary in some ways that will be handy for the entire rest of the course. So first thing we're going to talk about are some key terms. The definition of a relation is a relation is just kind of any set of ordered pairs, can be presented a number of different ways. We can show a relation just as a set of xy ordered pairs like we've seen, or in a table, or even in a graph. But really kind of any mathematical statement, it gives us a relation. Not the most useful thing in the world. So we're really more interested in a specific type of relation called a function. So a function is a relation in which every input value, which for us is almost always going to be x, corresponds to exactly one output value. And these are very common in the real world because it's just kind of what happens most of the time. Like if you think about a company, right, and you think about a certain month, that month has exactly one amount of profit that that company made during that time. That input value, the month, has exactly one output value that goes with it. Similarly, if you think about like the students in a class, every student will have exactly one test score value that goes that they've earned on a specific test. The input value has exactly one output value that goes with it. And so these functions are going to let us do some things that are going to be very useful to us in this course. And so this is really what we're going to be focusing on. And in fact, it's in the title of the course. It's going to be really important. So let's look at a couple of sets of ordered pairs, and we'll talk about whether they're functions or not. So this first one here, we just have these three ordered pairs. This is very basic sort of relation. All of these are going to be relations. But the question that we want to think about is this a function or not? And the answer to this one is yes. We have an input value of 2 here, goes with the output value of 3. Input value of -5 goes with the output value of 7. Input value of -3 goes with the output value of 3. Every input has a unique output value that goes with it. So this is a function. Okay, this next example, though, on the other hand, is not, because here we have an input value of 4 goes with an output value of -1. And if you look over here, we have the same input value of 4 that goes with the output value of -6. This is the same input value that goes with two different output values. This cannot happen if you want to be looking at a function. So while this set is a relation, all sets really are relations. It is not a function. We can recognize that by the repeated x values, the repeated input values here in our relation. Okay, so now we're going to talk about another couple of concepts. They're going to be important in this course. The next one's the domain of a relation. Okay, and this is going to be the set of all the input values, which are going to be x's for us most of the time for a relation. Okay, and then similarly, we have this thing called range, which is the set of all the output values for a relation. So if you look back at some of these relations we talked about before, okay, like this one here, if we want to talk about the domain of this, okay, it's very easy to get for a set like this. It's just going to be a list of all the x values. So the domain for this particular relation is going to be 2, -5, and -3. Okay, so the domain's just a list of all the x values if you have a set like this. Can be a little more complicated when we have graphs. We'll talk about that in a few minutes. But for sets like this, not too bad. Okay, the range, on the other hand, for this relation is just going to be the set of all the y values. So 3 and 7. And then you notice this y value repeats. That's fine. Our y values can repeat. If you think about the example we talked about before, the students in a class, you can certainly have two different students in a class that get 85% on a test, right? So y values, output values can repeat in functions, okay? We don't have to list it twice in our range. In fact, it's not wrong if you put it in there twice. It's just kind of complicated and unnecessary. So we already have the 3 in there. We don't have to list it in there again. Okay. So that's how we're going to get the domain and range for sets like that. Okay, so let's look at some other ways that we can present this data and talk about some of the concepts we've been working on so far in these other types of situations. Okay, so for this problem, we have our data presented in a table with x and f of x. Okay, so when we're dealing with functions, we'll very often use this f of x notation. And what this is just a replacement for y. So this f of x is our row of y data for this table. And this function notation, we'll talk a lot more about it later in the course. Hopefully you've seen it before. It should be something that's review for most of you. But it is just another way to write y, but it's a powerful way that we're going to be able to do some different things with later on in the course. Okay, so when we're presented with data like this, we can talk our way through these same concepts that we've been dealing with before. If I ask you to list me some inputs for this function, okay, the inputs are just our x values. So we could list them like -7, -3. And in fact, if we wanted to be a little more thorough, we could list all of the inputs and we could get the domain for this function. So if I wanted to list the domain for this, okay, I would just kind of list out those x values, just like we did when the data was presented in ordered pair form. Okay, so that is the domain for this particular function that we're given here. Okay, similarly, if we were tasked for some output values, okay, those are just going to be our f of x or y values. So 5, 4, 12. Those are some examples of output values. If I was to ask you for the range for this function, I would just list all of the output values. So 5, 6, 7, 4, and 12. Okay, we do have this function notation here. So we do know this is a function, but one way to check to make sure a table of data like this is a function is that all of our x values are unique. So again, I know this is a function because I have unique x values for all of my points here in my table. We can also answer some similar questions about setup like this, where we have a graph instead of a table or a set of ordered pairs. But the idea is going to be the same. Let's say we want to find the domain for this graph. Okay, just remember what the domain is. The domain is the set of all the x values, all your input values for your graph. And so we're just going to list them. Like there's only 5 points here. And so when you have a kind of distinct set of points like this, we can just kind of list them out. So the domain for this graph is just going to be -4, -2, 0, 1, and 3. It's just a list of all of the x values that show up in our graph. And then similarly, we can get the range by just listing out our y values. So, and really you can list these in any order. We can just go left to right. We can start from bottom to top. Bottom to top is the way that I tend to like to think about range. So I'm going to list these out as -4, then -2, then 1, then 2. And you'll notice I did not list -2 twice. Again, once your value is in your range, you don't have to list it again. This is just a list of all the values that show up as output values for our function. Once we got it in there, we're good enough. Okay. So let's talk about taking a graph like this and determining whether this is a function or not. We can certainly list the domain and range for this no matter what, but we do want to be able to determine whether a graph is a function or not. And remember, the definition of a function is a relation where every x value has exactly one y value that goes with it. Okay. And so if I look at this -4, -2, there's one y value that goes with the x value of -4, one y value that goes with the x value of -2, one y value -2 that goes with the x value of 0. So this is a function, but if there's an easy way to kind of determine that graphically, if you have a setup like this. So what I'm going to do is I'm just going to kind of think about an imaginary vertical line that's running over here on the left. And then what I'm going to do is I'm going to take this and I'm going to kind of drag it across this and determine whether this will ever hit my graph more than once at the same time. No matter where I draw this vertical line, I'm going to hit this graph exactly one time and no more. Okay, so this is called the vertical line test. And it's an easy way to graphically determine whether a given graph is a function or not. So this is a function because my vertical line is never going to hit this graph more than once. Let's look at a couple of examples of things that are not functions. Okay, so here's an example of a graph that's not a function. And I know it's not a function because if I draw that vertical line, I can drag it across any of these other spots and it's okay. But if I draw that vertical line right here, okay, I'm going to hit two separate points on my graph. So when you're doing the vertical line test, if you drag that line across your graph and if at any point it hits these 2 points at the same time like this, then we would say that this graph fails the vertical line test. That means it's not a function. Okay, a couple of other examples, like you can have more complicated graphs. Like I can even draw a circle. Okay, and if I'm deciding whether this is a function or not, the answer is definitely no, because I draw a vertical line, it's going to hit that circle more than one time. So this is not a function. Very easy way to tell whether you're looking at a function or not. And then similarly, you can have a graph like this, kind of a curve. Okay, and this is going to be a function because any vertical line I draw is only going to hit it one time. So this is a function. So the vertical line test is a very useful tool that we can use to decide whether a graph is a function or not. Okay, so let's look at another graph here, one that I've drawn out a little more carefully than the last couple that I did. We're given this curve, okay? And the first question we're going to answer is this a function or not? And the answer is yes, it's a function. Don't really have to do any work to answer that. Because any vertical line, I'm not going to draw them. I want to be able to use this for other questions, but any vertical line I draw is only going to hit the graph one time. So I would say that the answer to this question is yes, it's a function because it passes the vertical line test. And it's fine if you want to abbreviate that VLT, the vertical line test, something we'll use quite a bit in this first lesson or two. So fine to abbreviate if you prefer. Okay. So it's never going to cross more than once in this particular graph. Okay, so now let's talk about how to find the domain for a graph like this. Like a lot of people's first instinct is going to be to start listing out -3, 3, and 5, but that's not going to work here because this is a graph that's drawn and every single point on this curve here is part of my function. So, there's an infinite number of them, in fact. Every single point on this is part of my function. Okay, so we can't list them out. So what we have to do instead is we have to use this thing called a domain or called an interval in order to get the domain of this graph. Okay, so what we're going to do to get our interval that represents the domain of this function is we're going to work our way across the graph from left to right. Remember, when we talk about domain, we're talking about input values. We're talking about x values, okay? And so we want to work, we know our x values run from left to right across there, getting from smaller to bigger. And that's what we want to do with our curve here. We want to work our way across the graph from left to right. So over here, this is my leftmost point. I want to start with my x value there. So this thing is going to start at -3. And then we're just going to kind of run our way across this curve, okay, until we get to our rightmost point, which in this case is going to be 5. Okay, and then we want to include both of those points in our interval here because they're real points filled in, solidly part of our graph. So we're going to use these square brackets to represent the fact that these endpoints are really part of our graph. Very similarly, over here at 5, we have a filled in circle there that is part of our domain. Okay, so we're going to use those square brackets there. Square brackets mean that these values are included in our interval. So what this means is our domain is going to run from -3 to 5 and include everything between those 2 points. Okay, so similarly, we can do the range. A little trickier. we got to remember when we're talking about range, we're talking about the y values, the output values, and those are going to run from the bottom of our graph to the top of our graph. So, you might think about starting over here, but that's not where you want to start. You want to look for the bottommost point on our graph, which is down here. So that's going to be the start of our range. And we don't want to use the 3 here because remember, range is the output values, range is the y values. So we're going to start at -4. Okay, and then we're going to run up to our topmost point. And again, we don't want to use this one because this one up here is taller. We want to go to our topmost y value, which is at 4. And then again, for this graph, -4 and 4 are both filled in circles, part of our interval. We want to make sure we're including those. So we're going to use square brackets there as well. Okay, so that's the idea for domain. We're thinking about the x values. We're working our way across the graph from left to right. Range, we're thinking about y values, and we're working our way from the bottom of the graph to the top of the graph. Okay, so next we're going to talk about how to find the domain for some equations that were given. Okay, so the thing to know is that for us in this course at this point in time, there's really only a couple of things that can cause us problems in our domain. Okay, we can't have zeros in the denominator of our equations, and we can't have negatives underneath the square roots in our functions. Okay, so if I have an equation like this, y equals 3x plus 6, very simple, that doesn't have any denominators and doesn't have any square roots in it, there are no problems in our domain. So we would say that the domain of this is all real numbers. Just means you can put in whatever you want for x and it will work. Okay, if we wanted to write this as an interval, okay, remember we're going across from left to right on our graph, and we can go to the left forever because we can plug all real numbers in there. When we go to the left forever, we would say that our domain starts at -infinity, okay, and we can go to the right forever. That means it goes to positive infinity. Now, we used square brackets before because those were values that were really part of our graph. Here, these are not values. And infinities are always going to get parentheses. We're not actually including a value as our endpoints here. So we use parentheses in that case. Okay, so for a situation like this where we don't have any denominators, we don't have any square roots, we can put anything we want in for x, means our domain is all real numbers. And if we're writing as an interval, we would go -infinity to infinity. Okay. Next, let's look at a problem where we do have a denominator. So if we've got something like this, 5 over x minus 4. Okay, so the key thing here is we know we can't divide by 0, right? You just can't do it. It's not allowed in math. It doesn't make any sense. If you divide something by 2, you're breaking it into 2 equal parts. You divide something by 0, you're breaking it into 0 equal parts. It doesn't make any sense in the ways we use math, right? So we need to make sure that the denominator here is not equal to 0. So that's what I'm going to do. I'm just going to set up a little equation, set my denominator, make sure it cannot be equal to 0, and then I'm just going to solve it. So just move the 4 over to the other side. So x cannot be 4. Okay, so this is our domain. X can be anything except for 4. Okay, now if we're going to write this as an interval, what we have to do is just exclude this 4 value from our interval. So we're going to work our way across the graph from left to right, and anything less than 4 is fine. So we're going to start at -infinity. We're always going to use parentheses when we use infinities or negative infinities. We're going to work our way across to 4, and we're not going to include 4 in our interval. So remember, when we wanted to include something, we used a square bracket. Here, we don't want to include it, so we're going to use a parenthesis instead. Okay, so next we're going to write the word or the mathematical way to say or is to use this union symbol like this. We don't want 4 on this side either, so we're going to make sure we don't include the 4. Okay, and then we're going to go on forever. Any positive values bigger than 4 are fine, and then we're never going to include them. So you can use the word or here, or you can use this union symbol between them to put those two intervals together. So complicated way to say we can put anything we want in for x except for 4. Okay. So finally, we can have a setup like this where we have a square root in our equation. So let's look at that. So we know we cannot take the square root of a negative number, not and get a real number anyway. So our domain here is going to be a setup where x plus 3 is bigger than 0. We need to make sure that those values underneath the square root are not negative. Okay. And then we're just going to solve. So we'll move this 3 over to the other side. We'll get x is greater than negative 3. Okay. So what this means is I can have any value bigger than negative 3 as part of my domain. Okay. So if we're going to write that as a interval, we're going to start at negative 3. We cannot include that. You notice this says strictly greater than, right? So negative 3 is not going to work here. So we're going to use a parenthesis to indicate that. And then anything bigger than that is okay. So we're going to go all the way over to infinity. Infinities, negative infinities will always get parentheses. Okay. So negative 3 to infinity will be our domain for this. Okay. Okay, so this lesson wraps up with a few application problems, word problems, where we're going to use some of the ideas that we've talked about with functions and domains and ranges to answer questions. Okay, so this question gives us a table with years and premium amount in dollars per month. Okay, and we're going to determine whether this is a function. Okay. And then we're going to talk about the dependent, independent variables and talk about why it makes sense to call this a function. Okay. So the first question is whether this is a function or not. And it definitely is. You can see in the table, every age only appears once. If we had an age that appears more than once, then we'd have a problem. But really, it doesn't make any sense for this to not be a function because you have an age and then you have a price that goes with it. It doesn't make any sense. It's probably illegal, in fact, to charge some 35-year-olds one price and then other 35-year-olds a different price, right? So every age has exactly one premium amount that goes with it, okay? And you'll notice that the premium amounts repeat. That's okay. The premium amount is our output value. Okay. Our definition for a function is that every input value has exactly one output value that goes with it. Every 38-year-old pays $11.65 per month, right? We don't have some 38-year-olds paying one amount, other 38-year-olds paying a different amount. Okay. So this is definitely a function. So again, the key here is that every age has a premium that corresponds to it. And, there's not multiple ages listed. The same age is not listed multiple times in this first column. So this is definitely a function when you use the age as the input and the premium as the output, which is what every business would do. I mean, it just makes sense. You have a formula, you put the age in, you get a premium that comes out as our output. And it's always going to be a function. So we can use the techniques that we're going to work through in this class on that kind of a situation. Okay, so there are a few other word problems, but hopefully these ideas will get you off to a good start with these questions. The key thing to doing well in this class is to let me know if you're having any problems at all, because I'm here to help. You can email me. We've talked a little bit about how to get a hold of me, and I'm happy to help. So please let me know what I can do to help as we go through the course. Have a nice day. Looking forward to working with you all this semester.